Today I'm going to talk to you about the mathematical modeling and kinetic study of the aqueous phase reforming of sorbitol. This work was done by Lisa McClear as part of her PhD studies at Queen's University, and the results were published in the Journal of Applied Catalysis A. So basically, we're always trying to find ways for energy, more sustainable energy sources, which is environmentally benign, doesn't pollute the atmosphere much, and hydrogen energy is one of the most promising options, for clean energy, because combustion of hydrogen will produce basically water, and it has got very high calorific value. It is currently used in the space shuttle for rockets, and it can be used also for fuel cells to produce electricity. One way of obtaining hydrogen is from biomass. And in order to extract hydrogen from biomass, there's the process of aqueous phase reforming, which we can reform the actual sorbitol, which is obtained from glucose. And the actual operating temperatures are quite moderate, 200 to 250 degrees. So in terms of energy consumptions, it's much lower in comparison to pyrolysis or gasification. Also, aqueous phase reforming produces less tar and coking of the catalyst. And the process basically, we know that basically encompasses steam reforming and water-gas shift reaction. Because at this low temperature of 200, 250 degrees C, water-gas shift will take place. So again, sorbitol is obtained from glucose, which is derived from biomass, hydrolysis of biomass, especially the cellulose and hemicellulose components of the biomass. It is also used in the medical, healthcare, and cosmetics industry. It's estimated around 1.2 million tons of sorbitol is being produced annually. Sorbitol, we're gonna also use it for the kinetic study because it has got the same number of carbon-to-carbon bonds and carbon-to-oxygen bonds. So to simplify more or less the kinetic study and make it a bit easier for us to understand all the mechanisms and enable us to derive a robust model. Usually the aqueous phase reforming takes place over heterogeneous catalysts. We use metals, nickel, palladium, monocatalytic or bicatalytic catalyst, and we can use different supports such as alumina, zirconium oxide, and cerium oxide. However, we know that such process will involve a large number of components as well as large number of reactions. So it is quite difficult and cumbersome to model the process with so many reactions, and it's computationally inefficient. Plus, there's the problem of parameter estimation when we try to estimate all the kinetic rate constants. So there should be a better way whereby we can simplify, make some assumptions, and obtain a kinetic model which is simple enough, but at the same time has got a high fidelity and high accuracy. So this is a schematic illustration of how sorbitol can undergo a number of reactions in parallel and series. So like I said, it's a nice formula molecule. We have basically the same number of CC bonds and CO bonds. It can undergo dehydration in the presence of acid and produce ketones, polyols, acids, and many other derivatives. These derivatives, they can basically, in the presence of hydrogen, they can hydrogenate to produce, again, an alcohol, which basically will repeat the cycles of reforming, dehydration, hydrogenation to produce alkanes. Another pathway is the reforming with water-gas shift to produce CO2 and hydrogen. CO2 and hydrogen also can react via the Fischer-Tropsch reaction to produce alkanes. Or this hydrogen can join this reaction pathway over here to produce, hexanes and other molecules. Also, sorbitol, in the presence of metal catalysts, you can end up with cleavage of the CC bonds and CO bonds to give you a large list of components, including CO, CO2, hydrogen, and alkanes and methane. So the way we tackle this study is basically we're gonna investigate the actual reactions pathways between 200 and 250 degrees. We're gonna try both nickel. Test with nickel, so monometallic, and bimetallic catalyst, nickel with palladium catalyst. And we're gonna try also different supports, so alumina, zirconium oxide, and cerium oxide. So we end up with 6 types of catalysts, which we're gonna try and analyze the overall reactions over these catalysts. Also, based on the analysis and the experimental work, we're gonna devise a kinetic model, whereby we're going to simplify the aqueous phase reactions, and we're going to lump them together. All the components in the aqueous phase will be lumped as a single intermediate, from which all other reactions will take place. And what we are interested in is we're going to predict all the mole fractions of the gas components, and at the same time we want to determine the evolution of sorbitol in the aqueous phase when the conversion increases over time. So the experimental part, basically we had to prepare the catalyst. We had nickel nitrate along with palladium chloride, and these were impregnated into aluminum oxide, zirconium oxide, and cerium oxide. They were calcinated, and once we finished with the preparation, the catalysts were subjected to a number of experiments to characterize the properties of the catalyst and try identify some reactions that will take place with a specific catalyst and the other reactions which are inhibited based on the occupants of the sites or active sites. So temperature program reduction was conducted on all the catalysts to inspect catalyst reducibility, check for the free nickel oxides in the system, and the hydrogen uptake, and at what temperature the maximum hydrogen uptake will take place. Also, we did CO chemisorption to identify the particle size and the CO uptake and the active metal sites of the catalyst. Temperature program desorption and oxidation to develop the adsorption-desorption isotherm to tell us whether we are operating in the nanoporous, mesoporous, or macroporous region, and also identify carbon deposits and hydrogen. And also we did electron microscopy to determine the actual crystal shapes and clusters for both the fresh catalyst and the spent catalyst. Most of the reactions that were done in a batch reactor. Basically, samples were taken from the liquid phase for GC analysis, and the gas phase samples were taken for, the actual gas samples were taken for GC analysis, and the liquid samples were analyzed with HPLC and total organic compounds. So these are some of the results for TEM imaging. The first one here is basically the nickel catalyst. It is showing square crystals with an average size of around 20 to 30 nanometer. This is when we inserted palladium for bimetallic catalyst. So obviously the structure has changed a lot. We went from square shape into rod shape, whereby the diameter is around 2 to 3 nanometer, and the length is 20 to 30 nanometer. So the graphs, the pictures on the right side, they show the spent catalyst, and obviously we could no longer see the original structure because of the deposited products and compounds on the catalyst itself. This is the chemisorption results showing the CO uptake and the average particle size from chemisorption as well as from TEM. So we're comparing both. And what we realized, or we saw, that basically with 0.25 palladium bimetallic catalyst, we had the maximum CO uptake of 110.4 micromole per gram, followed by 28% nickel, so 72.8. And these they had, for the CO chemisorption, an average size of 66.4 nanometer versus 20 to 30 nanometer from TEM analysis. And this one gave 7.5 nanometers, which is quite close to the range that we obtained from the TEM analysis of 10 to 20 nanometers. So from these results, we can tell that basically the bimetallic catalyst is much more active in comparison to the monometallic ones. And as far as the monometallic catalysts are involved, we have the 28% nickel on alumina is the most active among the other monometallic catalysts. Then for the TPR profiles, so we're having here 4 different types of catalysts. The most important ones we can see are, again, the 28 nickel on alumina and the bimetallic with palladium. So the 28 one gave basically a high peak of hydrogen uptake at around 700 Kelvin, showing a very high activity. And for the palladium one, the temperature was a bit lower, so the reaction took at a lower temperature. So palladium is more active. And at the same time with palladium, we can see that the distribution is narrower. We don't have 3 peaks as with monometallic catalyst. The 3 peaks, we can explain them. The first one is because of the nitrate, hydrogenation of nitrate. This is for the free nickel oxide, this is fixed nickel oxide. With palladium, they're all grouped together almost. So palladium bimetallic catalyst has got a much better activity as far as this reaction is concerned. This is the SEM images for the monometallic and bimetallic catalyst. We know from literature and other researchers' work, they specified that mass transfer limitation will take place if cluster sizes of 200 micron and above are used in the reactor. In our case, we had a cluster sizes of the size of around 20 micrometers. So we made the assumption that mass transfer doesn't influence the reaction. In other words, the process will be totally dictated by the kinetic mechanisms and the kinetic rates involved. These are the results for temperature-programmed desorption and temperature-programmed oxidation for the monometallic catalyst and the bimetallic catalyst. And for most of the catalysts, we can see that CO2 started to appear earlier instead of CO, and most of the time, the hydrogen peak and CO peak, they correspond at the same temperature. And for the TPO, we're showing that basically CO2 was generated at around 650 Kelvin, a lot of CO2, which shows that basically this carbon, which is strongly bonded to the structure of the catalyst. There was little CO removed by TPO. So by analyzing all these peaks, we can preliminarily identify what are the most inhibiting reactions, what are the reactions that are taking place over the catalyst surface, and devise ways to develop the mechanistic approach in order to obtain the kinetic model. So after doing the catalyst characterization, we moved into mathematical modeling along with experimentation. So we did the experimental in the batch reactor. We collected samples with GC and HPLC. And then we thought that we're going to basically use a lumping approach whereby we're going to use an intermediate component which will undergo a series of reactions which are shown in the next slide. So we are saying that basically the aqueous phase reforming of sorbitol, initially, automatically sorbitol will be converted into an intermediate oxygenate component. This oxygenated component will undergo two separate paths. So the first path, it will undergo reforming in water-gas shift, which is the conventional reaction. So we have the intermediate reacting with water to produce CO2 and H2. And then these two components will react via CO2 methanation or Fischer-Tropsch to produce alkanes. And the other path, the intermediate over here, will react with hydrogen and will give basically a water molecule. So it's basically called hydrogenation and dehydration. And I'm going to designate it by hydrodeoxygenation. Also, the oxygenated intermediate will also undergo dehydrogenation to produce hydrogen. And this liquid intermediate, again, will react with water and will be subject to decarbonylation, producing CO2 and hydrogen as well. And the last reaction is that the intermediate can undergo what we call hydrodeoxygenation with decarbonylation. So it's going to produce an alkane and CO2. So these two paths, we have basically CO2 generation, H2 generation from the path one, and also we have H2 generation and CO2 generation, and also methane generation in both pathways. So later on, we're going to compare and determine where does the CH4, where does the H hydrogen come from? Is it from the gas phase reactions, path one, or from the liquid phase oxygenated compounds in path two? So graphically or schematically speaking, again, I have the sorbitol, which is a nice molecule over here. It's going to automatically generate an intermediate component in the liquid phase. And this one will go along path one to produce methane via reforming, water gas shift, and methanation. And this here, the liquid components of the oxygenates will undergo 4 types of reactions. There is the decarbonylation with water gas shift to produce CO2 and another intermediate. There's the dehydrogenation to produce hydrogen and another intermediate. There is the hydrodeoxygenation to produce basically water and another intermediate. And the last one is the hydrodeoxygenation-decarbonylation. So I'm going to use these terms later on to identify which pathway is basically dominating and which one is inhibited over specific different types of catalysts. So another assumption we made is that we said all the reactions are basically first order in terms of the reactant. And most of the reactions, they take place on the surface of the catalyst. Besides, we are interested in the gas components such as hydrogen, CO, CO2, and in the sorbitol evolution over the whole conversion during the reaction. Further assumptions made were that no mass transfer limitation is taking place, and there's no thermal degradation or condensation inside the reactor as well. So these are the both simulation results, straight lines, and the experimental data and points. And we are comparing, hydrogen formation, CO2, CO with different catalysts, along with the gas conversion and the liquid conversion. And what we realize is when we are using monometallic catalyst, we are achieving very low gas conversion, and most of the components are coming from the liquid components in the reactor, so higher conversion for the liquid components. We changed also the temperature, went from 498 Kelvin to 523 Kelvin, and also the gas conversion was really low. Whereas, the conversion of the liquids was high and reached almost 80%, this curve. And also we noticed that, at low conversions, the H2 profile remained almost constant. Yeah, so we're not consuming much H2. Now, when we increase the nickel content, what we saw is that, we managed to obtain a high gas conversion reaching 100%. And because of that, we can see that the liquid conversion dropped to 0%. So it shows that the oxygenated compounds in the liquid phase were involved heavily in the reaction, and they converted, to produce gas compounds. Also, what we saw that at a high conversion, H2, the hydrogen was basically decaying over the actual reaction, because H2 was involved in the methanation reactions, and as you can see here, CH4 was increasing. Another one with the different catalysts, 40%, what we saw is that CO2 was decaying, CH4 was increasing. So again, it's a methanation reaction because CO2 with hydrogen is producing methane. So we can see with different catalysts, loading, etc., what kind of reactions are basically dominating over which in the gas phase. Now this is with bimetallic catalyst. So when we introduce palladium, okay, and what we realized also that by changing the initial hydrogen pressure, the actual profiles didn't change much, and the model was also able to capture these transitions as well. With bimetallic, we obtained higher liquid conversions, also increasing the load, also higher liquid conversions. It was always increasing. And then for the last one with cerium and zirconium, we achieved very low conversions both at the gas phase and the liquid. So they had a low activity. Now, we're grouping together gas phase with liquid phase reactions because we want to determine which one is influencing the production of gases. With monometallic catalysts, we saw that decarbonylation is the dominant reaction in the liquid phase. Same thing here, 5% loading at 498 Kelvin, that's 523 Kelvin. Decarbonylation is dominating. When we use bimetallic catalysts, it's the hydrodeoxygenation-decarbonylation which is dominating the actual reaction pathway for both temperatures as well. And last one, what we did is we compared the actual hydrogen formation by reforming versus hydrogen formation by oxygenates, the rate. Also, we did CO2 formation, same thing, by basically water gas shift reaction over CO2 formation from oxygenated liquids. And we did the same thing for CH4 and H2 consumption. And what we saw over here that, hydrogen formation maintained a ratio of 1, which is indicating that hydrogen during the whole path of the reaction was constantly produced by reforming, or path number 1. On the other hand, for instance, CH4, it started with a high ratio, so CH4 was produced by methanation, path 1, and as conversion increased or as time passed, the CH4 ratio decreased, showing that decarbonylation and dehydrogenation basically took over and dominated the reaction. Also here for CO2, when we are using bimetallic catalysts with nickel and palladium, you can see the CO2 formation was really high. So it was maintained at 1. This is water gas shift reaction. So these catalysts encourage the water gas shift reaction pathway. And the last one, when we are using cerium, and the pointer is no longer working. So when we use cerium, we saw that the CO2 is decaying over the conversion pathway. So it's basically consumed for... I use all of them. They're already exhausted. So this fourth one. Okay. So in conclusion, this is the first attempt whereby the sorbitol aqueous phase reforming was analyzed kinetically, and mechanisms and pathways were determined. The model was highly accurate. It was able to capture the actual profiles of the mole fractions of gas compounds, and basically we identified that the bimetallic catalysts were much more productive in terms of conversion to hydrogen and methane. And I would like to thank you and acknowledge that this work was done by Lisa McLear and other supervisors from Queen's University. So if you have any questions, please feel free to ask me now.
Okay, any questions? Question here?
Just a question for myself. Hydrogen normally in the end product, you need to put in hydrogen for the biomass. By this way, do you make economic sense?
Well, biomass waste. We use biomass waste. We're not using.
Yeah, can you go back to the diagram you tried to explain that?
Which one?
In the very beginning, you have an introduction. About 2 or 3 page. Third page here. I guess no. The forward. Yeah, that
this is the overall.
That graph. Can you go back to the graph?
Okay.
Here, in the end, you want to put in hydrogen, right?
Yeah, I mean, eventually you want to drive the process to produce more hydrogen as much as possible. But also what you can do is you can adjust the process to produce, for instance, methane or alkane, depending whether you want to produce chemical derivatives for feedstock, to produce petrochemicals, not only energy. Yeah? So if you're only interested in energy, fuel cells you produce, you try to maximize your hydrogen. If you want to make polyethylene or other components, you need methane and alkanes to start with. So you can adjust the process.
Okay, there was a question here.
My question was also related to the economics, and he touched already that. First of all, when you use instead of sorbitol, now the glycerol, that you do not, glycose, the glycose, because you produce sorbitol out of glycose by hydrogenation.
Yeah.
So some of your hydrogen is lost already.
Okay, yeah.
When you use now the glycol, yes, instead of sorbitol, what results do you get?
Obviously, with the xylose is much more complex. Okay, so we chose sorbitol because it's small, it's a simpler formula, and we expect, the mechanism to be much simpler. So we didn't study xylose.
Okay. I have my doubts about that. Next question is, sorbitol is a very valuable compound.
Yeah.
Because out of that you can make, as you mentioned in one of your slides, different materials which are in cosmetics and in healthcare and so on. And even more, out of sorbitol you can make by dehydration isosorbide.
Okay.
And isosorbide is even more valuable than sorbitol. And now what you do is you convert that in methane, CO, hydrogen, and so on. I think we have fracking gas,
there's always a trade-off.
Shale gas, and we can make that much, much easier than using such a high valuable compound of sorbitol.
Exactly. There's always a trade-off between, the energy producing pathways and whether you're going to make sorbitol for other purposes. So there's always a question mark regarding this. But this is the issue with alternative energy and sustainable energy. Everybody's trying to find a way to produce hydrogen or natural gas, etc. And so most research is going this way, but always there's the positives and negatives. That's why sometimes fossil fuels they still as the main energy sources nowadays. But probably when they deplete, then things will change.
Any more questions? One here.
Thanks for the talk. I have 2 questions concerning. First one is you use gamma aluminum to support the nickel, right?
Yeah. And
do you notice the formation of spin nano phase in your catalysis?
Mm-hmm.
The spin nano phase, whether it will
It's a nano size, eh?
Sorry, the
Nanoparticle.
formation of nickel and the alumina, you feel form another phase structure called spin nanophase. I don't know whether that reaction exists on your catalysis or not. No. And the second question about a tiny amount of this palladium can really increase the performance a lot. Can you explain why?
Yeah, but what we did, so according to the chemistry option, we used different lourens or palladium, and there was a limit, like, at 110. So this one produced, the largest CO uptake. So we assume that this catalyst is the most active one, okay? And also when we did the TPR, also we identified that this catalyst is basically giving the best result because of the lower temperature and the very sharp peak. So I would leave this one to the chemist. I'm not a chemist, I'm a chemical engineer, so they did the analysis. And
Okay, any more questions? Okay, thank you very much.
Thank you.